Yes.
Finish.
Okay, Ishrath, you can start.
Minimum. So let me share my. Hope you can see the screen.
Yes,
Yeah,
yes.
we can.
So the paper I chose to present today, the title of the paper is Deep Learning Techniques for Inverse Problems in Imaging. So this paper does not introduces a new method for solving this inverse problem. Rather, it is a review kind of a paper. So it reviews up to this 2020. So what are the techniques have been employed to solve these inverse problems in imaging? So this paper was published in 2020 in an IEEE journal. So before going into the paper, let me give a quick reminder about this inverse problem and the terminology we are going to use throughout this presentation. So first, imagine we have a 2D space and we have a vector called x. So this is our ground truth signal, and we have a transformation called a forward process. We will be denoting it by A. So in this case, let's say our transformation is to map this vector into this x-axis. So our forward process is going to be a transformation like that. So after the transformation, we are going to get a measurement called y. So so forward process is the transformation that is going from the ground truth signal x to the measurement y. So then what is the inverse problem? So inverse problem is if we have a measurement y, can we estimate the ground truth signal corresponding to this measurement y? So if we take a look at this forward process, so this forward process A can be linear or non-linear as well. And most of the time, this forward process going to be non-invertible. So in this case, it's obviously non-invertible. So for this vector, there can be infinite amount of solutions that could be ground truth vector. So how can we estimate the corresponding ground truth x? So that is the problem we are trying to solve in this inverse problem. So if we have some knowledge about the prior knowledge about this ground truth vector, so then we can achieve a good estimation. So like that's like an overall reminder of this inverse problem. So now let's see what are the common inverse problems in imaging domain. So these are the list of imaging inverse problems listed in this paper. So for example, let's take a look at this super resolution imaging. So in this imaging modality, the forward model is going to be modeled by a subsampling operator. So that is kind of like a dimensionality reduction from the ground truth image to the detected image. And we also have a blurring operator. So the forward model will vary according to the imaging modality as well. So let's have a quick like review on this anatomy of the inverse problem. So if we have a ground truth image for a signal, which is going to be a higher dimensional signal than the measurement signal. So we can model the forward process like this. So if we have like an additive noise, we can model it using like plus epsilon kind of an equation. Or else if we have like a non-additive nature of noise, we can model it using a noise process. So traditional way is to solve this problem is to minimize the cost function to find out a good estimate for the x. So this cost function has two terms. One is the data fit term, and the next one is regularizer. So data fit term denotes how much the estimate matches the measurement y, and the regularizer determines like how well the estimate is going to behave in the distribution of our prior knowledge in X. Like, for example, so if we have a prior knowledge like our ground truth image is going to be sparse in a wavelet domain, so we can design the regularizer with L1 norm of the ground truth image in the wavelet basis. So, so this kind of problems traditionally uh, the traditional solvers are like iterative solvers, which uses gradient descent algorithms. So, so they will iteratively find estimates of x until convergence. So, but there are some limitations in those kind of solvers in certain conditions. So, let's say if we don't know the distribution of the signal, or we don't have like a clear prior knowledge of signal, in that kind of a scenario we cannot model this regularization. And if we don't know the forward operator properly, then we cannot model this data fit term. And also these iterative solvers are computationally expensive because we need to iterate until convergence. So these kind of limitations in the traditional solvers leads to in exploration of deep learning techniques to solve these kind of inverse problems. So in this paper, what they do is they like categorize the problems and provide like a taxonomy to like different kind of categories of problem, and how like previous approaches have been approached to solve these problems. So there are two kind of categories mentioned in this paper. One is based on the knowledge of this knowledge of the forward process of the imaging. For example, how much amount of we know about this forward process. And the next category is based on how much of or how kind of data we have for training these deep learning networks. So like if we have only the ground truth images, or we just have the measurements only. So in this paper summarizes so what are the approaches uh, to solve these kind of problems. So these highlighted are the ones that they are talk on this paper. Let's summarize these one by one in the future slides. So far everything is all right, right?
Yeah.
Okay. First case is we know the forward model fully during both training and the testing period. In that case, this is the most basic and most easiest reconstruction problem, where we have x and y in pairs. So for this kind of problem, there are two approaches. There are two approaches that have been deployed to solve. The first one is this network architecture. So here, what they are doing is given a measurement y. So if we know the forward model, so we can find an approximate inverse to this forward model, and we get an approximated initial estimate of x in this stage, and that approximated inverse is feed through this network is to ultimately arrive in the ground truth image. So the interpretation can be thought of as like this network learns the residual between the initial estimate of x and the final estimate of x. So before speaking on the pros and cons of this architecture, let's also see the next one as well. So the next architecture is trying to mimic um, the gradient descent with proximal mapping. So let me quickly like remind what is gradient descent and proximal mapping. So in the iterative solvers, so this is the like equation for gradient descent based iterative iteration. So to estimate the next estimate, so we are using the residual we have from the current estimate and we project it to the signal domain, and we do the gradient descent step. After getting the initial estimate from this gradient descent step, we do a proximal mapping. So this is where uh, we take into consideration of this regularization. So we are trying to find an X that also has desirable properties uh, in the ground truth image, as well as it fits the initial estimate given by this gradient descent equation. So this neural network architecture is trying to capture this proximal mapping happening here. So let's say if we are not clear about this regularization and we don't have a clear prior knowledge on the ground truth image, we can use this network to learn about the prior knowledge, or like learn the regularization needed to reconstruction. So that is going to be the interpretation of this uh, deep unfolding neural network. So these kind of structures are called deep unfolding neural network. So if you take a look at like the pros and cons of these network architectures, first the pros are going to be like for this one. So if we have like enough data x and y and sufficiently complex architecture, we'll be able to like easily find out the inverse mapping between the y and x. But the problem is going to be this model is going to be heavily relied on the forward model, the forward process. So if in some case we need to change the forward model, then we have to retrain the whole network from scratch, from the beginning again. So that is going to be the case for this architecture also. Then let's move to uh, a more harder case where we don't have the ground truth images. We only have the measurements in our hand to train the model. So in the paper, they have they mentioned an approach based on this sure estimation method. So which is short term for Stein's unbiased risk estimator. So if we consider a simple problem of denoising, so which is going to be can be modeled with this equation x plus epsilon. So ultimately, we also have a estimator for a trainable denoiser f theta. So ultimately, we have to find out this denoiser f theta that minimizes the error, and minimizes the mean square error between the ground truth and the estimate. So in this Stein's paper, what they have found out is, so this mean squared error can be uh, this mean square error is equal to this term in the right side of the equation. Like if we have a look at the right side of the equation, we don't see any x term here. So if then we if this f theta is trainable, then we can ultimately come up with a denoiser that finally trying to denoise this measurement y into the x. Because if we reduce this first function, it will reduce this one too. So an extended version of this sure is called G sure. So this equation is for only for the denoising problem. If we have a like more generalized forward model, so this is the equation for more generalized forward model. So yeah, downside of this cons of this approach can be like we are only relying on the so we have to first of all we have to know the noise statistics, otherwise we cannot model this equation. And uh, and the next thing is we don't have any idea or prior knowledge on the um, ground truth signals or ground truth images. So we this model is not interpretable. So we cannot like it doesn't make sense how it's going to work in a more general way. So it may be work to like a denoiser problem, but it is hard to generalize it to a uh, more complex reconstruction problem. So the next main category is
Ishrath, if you go back,
yeah yes
so here, like you say, like what if for any arbitrary a, this G sure doesn't hold.
yeah so if we can model the A linearly, then we can this equation is true.
Okay.
But if it is a very complex forward process, then this is not possible.
So if A is nonlinear, it is not. Is
Yeah.
that what you by complex process?
Yeah.
Okay, but still you need to know A. If it is even if it is linear, you need to know A.
Yeah. Without the knowledge of A, yeah. Not possible.
Okay.
So the next category is so we know the forward model only at the test time. So the meaning of this is we don't have like any knowledge on the forward model when training. So let's say if we have like bunch of ground truth images X, so there is no way we can find the pair of the Y for these ground truth images. So in that case, the most popular way to tackle this problem is learning a generative prior for this ground truth images. So how we can so learning a generative prior meaning is like to learn the statistics and the behavior of the ground truth of the excess. So how we can do is there is an approach called compressed sensing using generative models, CSGM. So the generative models are basically can be used to generate or to represent high dimensional data from an input given by a low dimensional uh, data. So if we are managed to train a generative model that can like if the uh, from the train set of x from a uh, very low dimensional input data, we will be able to learn the distribution of x. So once we have like learned the distribution of x, then the problem of estimation of the reconstruction of corresponding to the y falls into a very low dimensional problem. So then we can solve this low dimensional problem using a gradient descent kind of an algorithm. So here what we are trying to do is trying to find the low dimensional vector z in the latent space so that it generates the matching estimate that will lead to the measurement y. So that's the generative prior approach. Now let's take a look at the case when the forward model is partially known. So what is meant by forward model is partially known is, let's say our forward model is characterized by a few parameters, and those parameters have some some statistical distribution, and we know this distribution. So in some sense, we know about this distribution of the forward model, but we don't know the exact forward model of the image. So in that case, also if we have a bunch of ground truth images x's, we cannot generate paired measurements of y because we don't know the exact forward model. So let's say if we have like unpaired x's and y's. So in this case, we don't know the joint distribution of the x's and y. So given an x, what is a y? So given an y, what is x? We don't know that information, but we have the information of marginal distribution, marginal distribution of x's and y, how the x behaves and how the y behaves. So in order to tackle the reconstruction problem, we have to, however, learn the joint distribution of x and y. So ultimately we have to find out in the test time for a given y what is our x. So in order to find the joint distribution of the x's and y's, so one approach they mention in this paper called cycle GAN. So in the cycle GAN, what they do is they learn two generative models. So one generative model is to map x's to the y domain and y's from the x domain. So at the same time, we have to also make sure that this g and f's are inverse of each other. So what is meant by this inverse is, I'm sorry. So what is meant by this inverse is, we have a ground truth image x, and we put it into the like this f generative model, and we end up the corresponding y, and then we apply this g generative model, then ultimately we have to end up in the x. So when training these generative models, uh, if we model an additional loss term like this, so which induces the inverse property of f and g, then we'll be able to simulate or find out the joint distribution of x and y. So after the training process, we have f's and g's. So when testing, we only have to use the g. So given a y, we can find out what is the x. Let's move on to the next.
So Ishrath, if you go back.
Yeah.
So here, like, is it, so f and g has to be inverse of each other, right?
Yeah, correct.
Is it like imposed, like, or is it like not imposed, strictly imposed? In the sense,
So
like, is
yeah, so we cannot make it like strictly imposed because there can be like dimensional reduction in the x to y. So they'll be like x approximate.
Okay, okay, so it is okay, I see that makes sense. Mhm.
So ultimately, what we are like trying to induce some to find out the joint probability of it. So moving on to the next main category, next subcategory of this forward model partially known. When we don't have the y's, but we only have the x's. So in this case, it becomes more harder because we don't know the exact forward model, so we don't have y's in our hand. So in the training phase, we are again going to use generative priors, but for the forward model too. So we are going to have two generative models for generating ground truth images, and we are going to have a generative model to generate our forward model as well. So since we have some statistic about this forward model, so we can simulate a bunch of various forward models using those statistics. So we will be ultimately able to find out the distribution of the forward model. So after we train these two generative models, then we come back to the solving this mean square problem in the low low latent low dimensional latent domain. Then we can solve it using iteratively. So one thing I forgot to mention about these kind of generative priors. So one a con of this method is, so first of all, the generative priors are going to be very sensitive to training images, the training data. So if we train this generative model on the training set we have, and so it will be very overfitted to that training data. So if in any cases, if we have an outlier coming in, then it will be not captured in the testing time. Another thing is after training this model in the test time also, we have to solve it in a iterative way. So using a gradient descent algorithm. So that will also take some time to solve this problem. So it is also going to be computationally expensive. So let's move on to the next. Let's move on to the next category. So in this slide, we try to reconstruct from the ground truth images. Now it has become more harder. We only have the measurements with us. So how to tackle this reconstruction problem? So this paper provides two approaches. One is a supervised approach called noise to noise. So in this noise to noise work, they have a training data consisting of X tilde and Y pairs. So what is this X tilde meant by is, so this is the noisy version of the ground truth image. So we don't exactly have the truth image, but it is a noisy version of our ground truth image, and we have this condition as well. So the average for this noisy X for a given Y is going to be exactly the ground truth image. So under these conditions, so this work have trained and reconstructed with these kind of loss function. So they are trying to minimize this objective function. So this f theta is the trainable network or trainable estimator. So this f theta is trained to minimize the mean squared error between the estimator and the x theta. So one thing in this approach is like if we have for a given y, if we have like several x tildes, several different x tildes, then we can ultimately achieve a good reconstruction quality, because we know for a fact that for a given y, the expectation of this noisy x is going to be the ground truth. So there are so that is going to be the con of this method. So with only one kind of this pair, this reconstruction is going to be noisy. So to make it more quality, we need several pairs for each measurement. The next approach is an adversarial training called ambient GAN.
One question about noise to noise. Is there a generalized version of noise to noise? Like, so this is only like for denoising, right? It's not for any forward model.
They haven't like explicitly mentioned about that in the paper. I also didn't like dive into this noise to noise paper as well. So I actually don't have an idea about this is generalizable or not.
See, yeah, good. I just asked because I think like some of us were interested in looking into like whether you can use noise to noise for inverse problems beyond denoising. So I think it's an interesting approach, and also this noise to noise paper is also very nice if you want to read later.
Yeah.
Okay.
So continuing with this ambient GAN. So in like when in the cases of generative prior problems, we always trying to learn the distribution of the ground truth images. But in this ambient GAN problem, what they try to learn is the distribution of y, the distribution of measurement. So how they are going to learn the distribution of y is from generative and discriminative networks. So the intuition behind this network is like we have a generative network. So
Ishrath, we can't hear you properly. Can you?
hello.
Yeah, now it's better.
Yeah, can you hear me clearly now?
Yes, now it's better.
Okay. So in this ambient GAN paper, they are trying to capture the distribution of y, the measurements, rather than capturing the distribution of ground truth images x, like in the previous method I have. So how they are going to do is they are going to use a generative discriminative network. So the intuition behind this approach is, first of all, we have a generative network. So this generative network maps the low-dimensional data space into the ground truth space. So output of this is going to be a ground truth image space, and we apply the forward process so to that ground truth image. But actually, we don't know about the don't know about the forward model. We only know the statistics of this forward model. So in this case, they have an assumption that we can easily sample the forward model from the given statistics of the forward model. So this is going to be an instance of a forward model. So we have a ground truth image here, and we apply the model to get transform it to the measurement space. and then the discriminator is applied on the measurement space. So ultimately, what the discriminator try to find out whether this belongs to the training data distribution of y using this training data. So ultimately, what we are trying to do is to train a discriminator and generator and discriminator model. So generator will be able to generate um, ground truth images that will be like able to transform into the distribution of y. So after training these generator and discriminator models, then we have this generator model like trained to um, trained to capture the distribution of ground truth images. So after training, we just have to solve this like optimization problem of the low dimensional space. So this is they do it in like a kind of a smarter way, like with only having the like measurement. So, yeah, that's training from the only from the measurements, right? The final case is when we don't have any information about the forward model at all. So in that case, so the other cases like having only the x's and y's to train will be like extremely hard to train a reconstruction network. So in the paper they say that for now they have only, for their knowledge, they have only like have this case been analyzed on this unknown forward model case. So they have mentioned the framework called AutoMap framework for XY pairs. So like seeing on top, what we can observe is they are trying to capture the inverse mapping from Y to X from this training pair. So they have like a fully connected neural network in the first stage and a convolutional deep neural network in the second stage. So in the first stage, they are trying to extract like intrinsic features of the measurements from this fully connected network, and using that intrinsic like features, then try to reconstruct the ground truth image. Yeah. So that's all the categories and like works discussed in the paper as a summary. And finally, they have also, so this is the paper published in 2020. So these are the future directions they have mentioned in that time. So first one is control over the forward model design. So all the paper mentioned in this review paper, the forward model design is, they are like fixed. So they are based on the physics of the imaging modality. So one thing they like telling to try is to make the forward model learnable too. So we will have a good reconstruction quality because we also try to learn the parameters of the forward model as well. And so until that time, so there have been not much research done on this nonlinear inverse problem. And another thing they mentioned is called uncertainty quantification. So this comes into play into the generative model reconstruction. So in the for the case of like let's say generative priors, so we are trying to learn the distribution of ground truth images. So once we have learned the like the distribution of the ground truth images, um, so they are going to be bounded to those statistics, right? So if we have an actual measurement that came from an outlier ground truth object, so for that measurement also we will be going to get a good reconstruction, because the generative model ultimately will map to the good reconstruction quality images. So for that case, we will be not be able to find out like what went wrong. So in the like traditional iterative solvers, for that kind of measurement, we will be getting a, ground truth with artifacts. But for generative bias, we don't get like a bad image. We'll always get a good image in the ground truth reconstruction. So this uncertainty quantification also, like they are advising to research in the future. Yeah, like that's all in that paper. I wanted to like present. Thank you.
Do you have any questions? Yeah, so I have a question about the statistics of the Ford model. So when you said the statistics of the Ford model, can you give an example they discussed in the paper?
Yeah, so that thing they don't like give an example for the statistics of the Ford model. They just say that if a Ford model can be parameterized using some parameters, so and if the parameters have some statistical distribution, then we know the statistics of the Ford model.
See. Yeah, good.